Next, I will show how to apply the one mean z procedure. Consider the following example. An incubation period is a time between when you contract the virus and when your symptoms start. Assume that the population of incubation periods for a novel coronavirus is normally distributed with a population standard deviation of 2 days. By surveying randomly selected local hospitals, a researcher was able to obtain the following sample of incubation periods of 10 patients: 6, 2, 4, 3, 3, 7, 5, 8, 5, 7. Use the sample to construct and interpret a 90% confidence interval for the average incubation period of the novel coronavirus. First, let's check if all necessary assumptions are satisfied. The sample is simple random, checked. The population is normally distributed, check. The population standard deviation sigma is known, and sigma equals 2, check. Also note that the average of the sample is 6 plus 2 plus 4 plus 3 plus 3 plus 7 plus 5 plus 8 plus 5 plus 7 divided by 10, and it is equal to 5. Once the assumptions are verified, we may apply the procedure. We will use the following template to construct and interpret the confidence interval. In this problem, the unknown parameter is mu, the mean incubation period. The point estimate is the sample average, which we found to be 5. How confident are we that the point estimate equals to the population mean exactly? We are 0% confident in that. And we set the new level of confidence to be equal 90%, for which alpha must be chosen as 0.1, so that 1 minus alpha times 100% is equal to 90%. Then alpha over 2 is 0.05, and the critical value z alpha over 2 is z 0.05, which is equal to 1.65. Now we can find the margin of error by using the formula. 1.65 times 2 divided by square root of 10 is equal to 1.04. And we can compute now the lower bound, 5 minus 1.04, which is 3.96. And the upper bound, which is 5 plus 1.04, which is equal to 6.04. Now we can interpret the results. We are 90% confident that the average incubation period of the novel coronavirus is between 3.96 and 6.04 days. In addition, we may also answer the following question: how large the sample must be so that the margin of error is less than 0.25. To answer the question in part B, we will use the formula n is greater than z alpha over 2 times sigma divided by the desired margin of error, all squared, in which we can plug in all the given values to get 1.65 times 2 divided by 0.25 all squared, which is equal to 174.24, which must be rounded up to 175. 175 is the smallest sample size for which the margin of error will be less than 0.25. I just showed how to apply the one mean z procedure to construct a confidence interval with a certain level of confidence, and how to determine the sample size to achieve a certain level of accuracy.